So I wanted to back up just a little bit and um, give you another visual as to what we're doing in this lesson. And what we're trying to do is we're trying to find the instantaneous rate of change uh, associated with a function at any given point. And that's got a lot of practical applications in real life, and it's really any of the physical sciences um, that talk about things that change. You know, chemistry has a lot of change involved with it. Physics has a lot of change involved with it. Think about speed. What is velocity? Velocity is how fast your position changes with respect to time. Okay, so think about what acceleration is. Acceleration is how quickly you're speeding up. So, you know, how fast the rate of change of your velocity is what acceleration is, okay? So let's look at just a couple of, real overview, high-level overviews here. I think if you looked at a function that looks something like this and compared it with a function that looks something like this, I think you would probably agree with me that this function is changing a lot more quickly than this function is, right? In fact, if we come out to a point here and we draw a tangent line on that curve, we can see that the slope of the tangent line is significantly different than the slope of a tangent line on this curve, okay? And that's really what we're trying to discern here in section 12.3 is we're trying to figure out instantaneous rate of change. And as it works out, the instantaneous rate of change of this curve is given by the slope of the tangent line, okay? So we have a formula for that. And I'll go through a couple of examples, some more basic examples to help us understand that. So let's take the function y equals 2x, okay? And we should know y equals 2x is a line with a slope of 2. So, you know, we should be able to think ahead a little bit already and say that we know that our final answer is going to be 2, right? Because we are looking for the slope of this line. That gives us the instantaneous rate of change at any point along the line. So let's use our definition, the limit as h approaches 0 of f of x plus h minus f of x over h. Now we're going to substitute here because our function is not x, it's 2x. So what we've got is the limit as h approaches 0 of 2x plus h, not 2x, because remember it's x plus h, minus f of x is 2x over h. So if we distribute this guy, we'll get the limit as h approaches 0 of 2x plus 2h, right? I'm just distributing the 2 here, minus 2x over h. Now we can do some simplifying, and we see that this 2x and this 2x cancel, and we're left with 2h over h. Well, that's easy. The h's cancel, and we're left with 2. So the the instantaneous rate of change at any point along that line is 2. And that should make sense to us because we know y equals 2x is a line with a slope of 2. So the slope at any point on that line is 2. So we used our formula for instantaneous rate of change of a function to prove that the slope is 2. Okay, that may seem like, you know, going around your elbow to prove a point, but I wanted to show you a really basic example. And I'm going to show you one that's probably just as basic, but a little more interesting. It's still a simple function to think about. Okay, sorry if I'm going in and out of focus here. It's one of the features of this camera. Okay, so let's y equals x squared. Let's take a look at that one, and we'll do it the same way. We'll start with our definition. The limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so let's do our substitutions here. So we've got the limit as h approaches 0 of x plus h squared, right? Because we're just adding x in here, but the whole thing is still squared, minus f of x, which is x squared, over h. Now we have to FOIL this guy out. So let's go up here and FOIL x plus h times x plus h. So we get x squared plus xh plus xh plus h squared. Oh, that's a tongue twister. Okay, so let's rewrite this then as the limit as h approaches 0 of x squared, and we can call this 2xh, plus h squared, and don't forget our minus x squared, over h. Now we can see that these guys cancel, and we're left with, I'm going to skip the limit notation for now just to keep it easier, 2xh plus h squared over h. Okay, we can factor an h out of the top here, and I'm going to order this. Let's see. H times 2x plus, we take 1h away from h squared, and we've got that. Now we can see that we should be able to cancel these guys, and we're left with, I'm going to go back and add my limit notation because it's important here, the limit as h approaches 0 of 2x plus h, and if we do our direct substitution, h is equal to 0, we get the answer is 2x. So that gives us the slope of this function at any point on that function. So if we graph x squared, which we know looks like this, and we pick any particular x value, let's pick x equals 3, and we come up here and we draw the tangent line at x equals 3, I promise you the slope of that line is 2 times 3 equals 6. And this is the function that will give us the answer for the instantaneous rate of change at any x value along this line. So let's come over here and let's look at -4. What happens at -4? Well, we should see the slope of the tangent line is going to look something like this, and it's a little bit steeper than this. And we can plug in -4 here. 2 times -4 is -8, and that should make sense because our slope is negative for this tangent line. It's leaning left. It's a negative slope, and it is steeper than this slope was at 6, so -8 is our answer. That's the average, the instantaneous rate of change of this function at the point x equals -4. So we'll do some more exploration of this as we get on in this section, but this is just two simple examples to help us understand what this definition is and what we're actually trying to accomplish by using this definition. And then a little bit later, I'm going to relate this to another term that tells us about instantaneous rate of change, and that term is derivative, and we'll learn what the derivative means in the next lesson.